So before we talk about how to take derivatives, I want to talk just a little bit about what a derivative is and how we can think about derivatives. So I have the definition of a derivative over here, but the way that I like to think about derivatives, aside from the limit of a secant function, a derivative is an operator. It's an operation that we do to a function. The same way that we have addition, subtraction, division, multiplication. Those are all operators that we can do to functions. So the derivative is an operator, it's an operation, and its symbol is dx. So the derivative is an operation that we do to a function. What is its output? What does it give us? When we perform a derivative on a function, it gives us a second function. And what we can do with that second function is use it to find the slope at any point on the original function. So a derivative is an operation that we do to a function that gives us a second function that we can use to find the slope on the original function at any point on the original function. An example of that could be the graph of x squared. Let's say that this is x squared and that this is definitely a parabola. So we have the function of x squared, and let's say that we want to find the slope at any point on the function. The way we can do that is with the derivative operation. So we can take the derivative of x squared, which equals 2x. This is our second function that we got out from the derivative operation. We can use this. We wanted to know the slope at any point, and let's say we want to know the slope of x squared at point 2. We can use our derivative here of x squared, and we can plug in the 2, and that will equal 4. So at the point of x equals 2 on the graph of x squared, we found that its slope at that point is equal to 4. So let's say that we have a function, the function that we just seen, f of x equals x squared. It's that parabola that I just talked about. We can also write this as y equals x squared. So how do we take a derivative of this function, x squared? Probably guess that we have our derivative operator, and then I'm going to make some brackets. I like to use brackets just because they look nice. So we're going to write our function inside of the derivative operator. And then we're going to need to establish some rules about how to take derivatives. With any math operation, addition, subtraction, multiplication, you need to have rules, and that just makes life easier. Our first rule, this is sort of going to be an aside, we'll get right back to this function. Our first rule is taking a derivative of a constant. A constant meaning any number or value any number that doesn't change, that doesn't vary. If we take a derivative of a constant, it's going to equal 0. The reason that is because if we have a graph here, and then we have a function that is constant, so like y equals 1, if we graph that, that might look something like this. Just imagine that's a straight line. The derivative is about deriving a function that gives you the slope at any point on the original function. If we have a straight line, the slope is going to be 0 everywhere. So when we take a derivative of a function that is equal to a constant, it's going to equal 0. So that's our first rule. And we can just call that the constant rule. Our second rule is actually going to help us get started with taking derivatives. The second rule is called the power rule, and it tells us that with any function to the power of n, it is equal to n times x to the n minus 1. That is our power rule. It's what we're going to use most of the time, at least when starting with derivatives, or even well into derivatives, you're going to use the power rule all the time. So just with the power rule, we can see that we could solve this derivative right away because it fits. We have x to some power, and then our rule here is x to something, and if something fits your rule, you can do it. So we can use the power rule to solve this derivative. We can see that 2 is going to be our n. So now we can apply the power rule to this derivative by writing out this bit here. So n, which we know is 2, times x to the 2 minus 1. That is going to simplify to 2x to the 2 minus 1, which is 1. And then x to the 1 is just x. So we're left with 2x. And that's exactly what we saw on the previous page. So what if we have a function like x cubed? We can see that like x squared, the function x squared, it matches our formula for the power rule. So we can just simply use the power rule again to solve x to the cubed. And we can do that by writing out d dx x to the cubed. You don't have to have brackets or parentheses around the function, but it keeps things clean and could prevent you from making mistakes in the future. So we have our derivative written out here, the derivative of x cubed. Just by looking at it, we can see that it matches the power rule. And with the power rule, we just need to figure out what the exponent is, and it's obviously 3. So our n is going to equal 3. And then we can follow the formula to take this derivative. And that is n, which is 3, times x to the 3 minus 1. And simplifying, get 3x squared. And so you can kind of see a pattern here with applying the power rule to simple functions like x squared equals 2x, and then x cubed equals 3x2. And you might see the pattern developing here. If we had x to the 4th, and based on this pattern that we're seeing here, you might see that we can simply bring down the 4, bring down the exponent, write our x, and then just subtract 1 from the exponent. That's exactly what the power rule is. So functions that is x to some power, It's very easy to work out in your head once you see it a couple times. And of course, all of these have a ddx in front of it because we're taking a derivative. So what if we have a function like this, where we have our x cubed, which we just did, that was 3 to the x squared, but multiplied by a constant. And that brings us to our next rule. When we're taking a derivative of a function that is being multiplied by a constant, we can rewrite the derivative by pulling the constant out of the derivative and then taking a derivative of our function. This is called the constant multiple rule, where we can just simply pull constants out of a derivative and then multiply the result of our derivative by that constant. You might be tempted to think, oh, we have a constant rule. The derivative of a constant is 0. Wouldn't the derivative of 2 to the x cubed, wouldn't that be 0 and then multiplied by the derivative of x to the cubed, which would equal 0 because we're multiplying by 0? That's not the case, because this is not the derivative of a constant function. This is the derivative of a function that has a constant multiple in it. And our constant multiple rule says that we can pull the constant out of the derivative. So let's see what that looks like with 2x cubed. Well, we know with our constant multiple rule that we can bring the 2 out, so we will bring the 2 out, and then we will multiply that by the derivative of x cubed. Bring this down. We have 2 times the derivative of x cubed. We know from our power rule that we're just going to bring the exponent down and then subtract 1 from the exponent. So we'll have 3x cubed and get 6x squared. That is our answer. And that's how we deal with constants. Let's say we have the function x cubed over 2. So you might think that this function does not quite fit our rules here, but this x cubed over 2, we can rewrite it as 1/2 x cubed. So when we want to take a derivative of this, we can pull that 1/2 outside of the derivative and take the derivative of x cubed, which we already know is going to be 3x to the 2. And then you can simplify that to 3 over 2x squared, or 3x squared over 2. Our power rule also works for negative exponents. So if we want to take the derivative of x to the negative 2, we just follow the power rule. But we need to keep in mind that we are dealing with a negative exponent. So when we bring down our n, it's going to be negative. So if we take the derivative of x to the negative 2, we bring down that exponent. We have our x, and then we subtract 1 from negative 2. So that's going to be negative 3. Negative 2x to the negative 3. How about if we have a function that looks like this? The derivative of 1 over x to the 3. Well, if we just think back to our algebra, 1 over x is really just x to the negative 1. And in this case, 1 over x to the 3 is equal to x to the negative 3. What we can do here is simply rewrite we can rewrite this function to fit more nicely to match with our power rule. So we have 1 over x to the 3. We can rewrite that as x to the negative 3. And then we can perform our power rule. We're going to bring the negative 3 down. We have our x, and then we're going to subtract 1 from negative 3. So we're going to have negative 4. So what if we wanted to take a derivative of a function that looks like this? F of x equals 3x squared plus x cubed. To take a derivative of this function, we're essentially going to break this function up into two different functions, 3x squared and x cubed. And we're going to establish a new rule for doing this. So if we call this term 3x squared, if we call that f of x, and we call this term over here x cubed, g of x, our new rule tells us the derivative of f of x plus g of x, the derivative of that is equal to the derivative of f of x plus the derivative of g of x. All we're doing is taking each term by itself, taking a derivative of it, and adding them together. This also works with subtraction. We would just replace the addition with subtraction. So knowing that, the derivative of 3x squared plus x cubed is going to equal the derivative of 3x squared plus the derivative, plus the derivative of x cubed. We know the constant is going to come out, but there's no need to rewrite the constant on the outside. So we're just going to bring down the constant, and we know that we're going to do our power rule. So we're going to bring down the 2. It's going to be multiplied by the 3. And then we have x to the 2 minus 1, which is just 1, so 2x. That's this part of the derivative. Now we're going to add our addition. And then we're going to take care of this term here, the derivative of x cubed. So simple power rule, we bring down the 3, and then that's going to be multiplied by our x, and then we're going to subtract 1 from the exponent, so x to the 2. So we simplify this, we get 3 times 2x, 6x, plus 3x squared. That is how we deal with addition and subtraction in derivatives. So let's do one with subtraction. Let's say that we have y equals negative 2 over x to the 3 minus, let's say, 5x squared. So this one may look a little complicated, but our rules here are more than adequate for taking the derivative of this function. Start by writing out our ddx. So taking the derivative of negative 2x to the 3 minus 5x squared. So we're taking the derivative of a function that has subtraction in it. And we know from our rule over here that if we have a function that has addition or subtraction in it, we can break it into its terms, take the derivative of those terms individually, and then add or subtract them later. So let's start with this first term. We have negative 2x cubed. We want this to resemble our power rule as much as possible. And if you remember, 1 over x equals x to the negative 1. So 1 over x cubed is going to equal x to the negative 3. We can rewrite that as the derivative of negative 2. Our x is going to come up, and we're going to have that negative exponent. Now we can take the derivative of this term. We have this negative 2. That's our constant. We're going to pull that constant out, and then we can simply do the power rule on this x to the negative 3. The negative 3 is going to come down and be multiplied by the constant, the negative 2 that we pulled out. So the negative 3 is going to come down, and then we're going to have x to the negative 3 minus 1. Remember, we subtract 1. So we have negative 4. So we have negative 2 times negative 3. That's going to be positive 6. And then we have x to the negative 4. That was just the first term. We still have minus the derivative of 5x squared. We have to remember that we're subtracting these two terms. So the derivative of 5x squared, we can do this one on our heads. We know the constant comes out and it gets multiplied by the exponent that we bring down. So if we rewrite this, 6x to the negative 4, and then we have the minus. So we have 5 times the exponent that we bring down, so that's 10. And then we have x 2 minus 1. So that's just x to the 1 or x. So then our final answer is 6x to the negative 4 minus 10x. How about if we had something that looks like this? Y equals x cubed plus 7 minus 4. So just by looking at this function here, we know that when we're dealing with addition and subtraction for taking derivatives, we split each term and then perform a derivative on each term, adding and then subtracting later. So we can see here that the x cubed, that's our power rule, and why don't we go ahead and write that down, the derivative of this function. So to take this derivative, we know we're going to be splitting these terms individually and taking derivatives of them by themselves. So our x cubed, we've done this a bunch of times, 3x squared, and then we're going to be adding the derivative of 7. The derivative of 7 is a constant, and we know the derivative of a constant equals 0. So we're going to have plus 0, and then we're going to have minus our last term, the derivative of 4, which is just another constant. So that's going to be another 0. So then we're left with 3x squared. One final comment on notation. So we've been working with the derivative operator, ddx, of some function. This is the operator that tells us to take a derivative. The same way the division operator tells us to divide, and the addition operator tells us to add. The ddx is an operator. Let's say we have the function y equals x squared. This whole time, we've just been writing down our ddx of the function x squared. To get a more complete picture of what a derivative is, when we take a derivative, this derivative here, we get 2x just equals 2x. That we know that's our derivative, but it's not attached to anything. So to get a complete picture, we want to take a derivative of both sides of the equation. And to do that, do our ddx of y and our ddx of x squared. We get dy dx equals 2x. Now our answer here, the derivative, is attached to something. Dy dx, derivative of y, equals 2x. Now this dy dx, this is really our derivative. This is our label for the derivative of the function y. And this dy dx can also be written as y prime. If we have y, the derivative of y is y prime, or dy dx. These are both ways of writing the derivative of the function of y. So just to clarify, ddx is our operator of some function. Dy dx is actually the derivative of that function, whatever it equals. I hope this video was a helpful introduction into taking derivatives and memorizing these basic rules of differentiation that build upon derivatives in calculus. This is the first video in a series of videos that I'm going to be making on derivatives and other topics in calculus. In the next one, I'm going to cover taking derivatives of trig functions, more complicated functions, like the second one here, derivatives of quotients and products, all kinds of stuff. So I hope you enjoyed watching. I hope you learned something, and consider subscribing for future videos on calculus, and I hope you have a good day.